Hello everyone. I'll be going over a deeper dive into my 60-bit RAM and in particular just one D flip-flop cell and kind of the modifications I've done to implement it into the RAM. Um, so I think it's much easier to see this from a circuit diagram perspective first, and then we can see how this one-for-one was made in Builderment. So, the basic building block that I have in Builderment is NAND gates and inverters. So, when I originally made my design, I looked up one online for a D flip-flop that utilized only NANDs and inverters. So on the right here is our D flip-flop. So the base of how this works, and I'm sure there are better videos online of this, is you have two outputs, your Q and your Q bar. So whatever is stored in this RAM will have two outputs. So let's say we have a 1 stored in this D flip-flop, then Q will be 1, Q bar will be 0. If we have a 0 stored in this D flip-flop, we'll have a 0 output and a 1 as the Q bar. And more or less these lock each other so that if there is a 1 here, it feeds into this NAND, forcing this one to be 0, unless there is some change elsewhere in the circuit. So the inputs of this are the clock and the data. So one requirement is in order to write the data, we have to have the clock signal go high. So this clock signal has to be 1, and the data can be whatever you want to set the DRAM to. So let's say the DRAM is currently 0, and clock is 1, and then data becomes 1. Your DRAM will then store a 1 inside. If the clock is low, and that same situation happens where the data is high, nothing happens. So we'll still continuously output this. So as for my Builderment implementation and turning this single D flip-flop into a network of 60 bits, we have my design here on the right. And this is very simple, where this is our Q up here. This signal down here is the clock, and this signal here is the D input. So more or less, if this bit is enabled, then the signal will go through. If it is not enabled, the signal will not. So if this is a 0, then the output here will be 0. And then what I have implemented is all my my cells are connected. So anything, like let's say this was the least significant bit, I would have all 15 of my D flip-flops least significant bits ORed into each other. So just imagine that this is another one. What would happen is I would only have one being enabled at a time. So let's just say this one is the only one that is 1. And then this is 0, this is 0, this is 0. And we'll say a 1 is stored in here. And a 1 is also stored in here. All of these get ORed together. So what happens is this will output 0, this will output 0, this will output 0. Oh, actually, well, one thing is I have two sets of bars here. So what would end up happening is this signal and this signal would connect, and this would be my output. And then this signal and this signal would be my other output. So I'm only having one of these read registers on at a time, so only one gate will be active into that OR. So this would be 0, 0, 0, 0. It'd get ORed, and we'd see we'd have an input of 1 here and an output of 0 here. So that's kind of the base of how this works. And then for the implementation in Builderment, it was just kind of taking this circuit and making sure everything was hooked up correctly and compacting it a fair bit. So here is my Builderment. So let's see, this whole section up to here is this image here at the top right. So this is one cell. And similar to the image, we have our D input here for our write, and we also have a line for the address select here, or in this case it'd come out of the decoder. So this write enable will only be on when my decoder says it should be. And then we have these two lines, which are my read for my A output, and then we have these two lines down here for my read B output. So that corresponds to this bit here and this bit here. Once everything's output, right? These are the input addresses. Yeah, and then the reason we have two lines for each signal is my whole system is based off loops. So if we just want to see kind of where some of this goes, where's a good signal? Yeah, so we can have this D input be an example. So right now I'm saying, okay, write a 1 into the most significant bit of all my D flip-flops. But none of them have the write enabled, so nothing happens. But here we have this loop here. So this will go down through here. This is an input to one of my NANDs. And then it'll continue that pattern for every single NAND in the array here until we get all the way down where it loops back around. And then we'll be able to see all the way back up here again. That it then goes through this chain here and goes into an inverter. So that is the D input there. For, let's see, that would be the D input of the actual D flip-flop. So one goes into an AND gate, one goes into an inverter. And then that gets looped around and goes into my inputs. So if we track these two lines, these go in through here, and this is where I control it. So if I delete this gate, this conveyor belt here, the line stops. So this is flow-based, so I've stopped the flow, and it takes some time for that to propagate throughout the whole system. So if we wait a few more seconds, this line will eventually stop as well. And as the amount of gates I have connected to this, the longer it takes, because there is some propagation delay, and just how these gates are made lends itself to an increase of propagation delay as well. And there we go, the gate is stopped now. So now it is in a solid 0 position. And as we can see here, the display also updates. So this only updates once everything has reached a steady state. So let's turn this back on and we'll see how I implemented the rest. So we've shown this D input here. So that gets fed into a NAND gate. So that's the S NAND gate shown at the top right. And then we have that being output into our top right Q NAND gate. So let's see where that connects. So this is the output of the gate. If we follow it around, we will see inputs into this gate here. And let's see. Yeah, so this is one of the inputs into that NAND gate. And then this NAND gate gets output here. Let's see. has been a while since I used this circuit, so let me just see. Yeah, but let's see. Yeah, so these are my Q and Q bar. So right now, currently, we have let's just see what we have stored in here. We have a 0 stored in this register, as shown by that bit there. So let's see, where was I? Oh yes, here it was. Okay. Yeah, all these start to blend together and look the same. But yeah, because we have a 0, our Q bar is high right now, and our Q is low right now. And then these Qs get output based on the read registers. So right now we have both RA and RB off right now. So why don't we turn those on and see what happens. So I will set it for that first register. So we'll just turn RA on for now, just so we can see the difference. And while we're here, we can see it propagate. So this one will eventually, this one here will eventually turn on based on this set of a 4 input NAND. Oh, whoops, I had this one turned on still. That's why. I was wondering why it was taking a while there. Yeah, so we'll expect this line to turn on, and that should block all 4 inputs into this NAND. Oh, something broke here. Okay. Yeah, this happens sometimes if these storages get full. Normally they don't, but I guess I did not clear this one out fully. So let's fix that real quick. Oh, it's because I was still feeding it new plates, so I guess that was from when I was originally loading it up. For now, we'll do that there. That should fix it. Yeah, and now all the signals are blocked, and this signal has started to flow. So our read is enabled for this signal. So as we can see, this line has started flowing. So perfect. And as we can see, now that this read is on, let me switch my image in the top corner to this one here. So now that read A is on, that feeds into a NAND gate, which is NANDed with the Q output. So let's see if we are right. Yep, this is connected to this output here. There we go. That's a good way to select it. Yeah, and then we should expect that the display over here should have a 0 in the most significant bit, and it does. Yep, see it matches this whole register exactly now for all 4 bits. Okay, now why don't we try changing the bit? So let's try writing to this register. So we can write a 1 to it. We can write 111 to all 4 registers here. So why don't we do that? So just need to select this. And that should take some time, but it should start propagating through. And this system is just a simple inverter system. So I have 8 signals. So I have the 4 signals here, but I also have their inverted counterparts, and I just run them through 4 NANDs based on which one I want, which one matches. So I would want a 0, 0, 0, 1 to be present for this NAND gate in order for that address to be going through the decoder. So as we can see, it's starting to be turned on here. It hasn't fully propagated because this belt's still off right now, but if we go over to the RAM, we should expect it to start propagating. Yep. So as we can see here, it is fed through here as part of the write. And we should expect our bit to flip. So let's see where our display is at right now. So it's still at 0, 0, 0, 1. We should expect it to switch to 1, 1, 1, 1 shortly. And we can even keep an eye out here. So this one was on before, but now it is turned off. This one is on now. So let's check. Well, this one actually updated first, but so our actual output register, or our output display, updated before our internal checker changed, which is kind of cool. But yeah, right now we're outputting 1, 1, 1, 1. And because I didn't mention it before, these are our outputs here. So these are all connected to every single other gate here. Every other D flip-flop. So this is kind of my special OR gate. It's not really an OR gate. I can quickly throw up paint and show you guys how it works. But it's not the best. So more or less it works for any amount of inputs. So let's just go 1, 2, 3. 0, 0, 1, 0, 1, 0, 1, 0, 0. And then we have stuff like this as well as our inputs. And then our output, in this case of 0, 0, 0 would be 0. In this case it'd be 1, it'd be 1, it'd be 1. And then all of these break the system. So it is not a very good OR gate. It only works if only one of the inputs is high or if all of them are low. So that's why I have some safety precautions where the address should be set to 0 in between different writes or reads. It doesn't fully break the system, but it would cause like minutes of delay later on. And that OR gate is simply done by connecting all these outputs. So if any of these are flowing, the output will flow. And that kind of makes sense, right? In Builderment, if one thing is flowing, you don't the full force of that flow will be present through the line. You only need one current sink in this case for current to flow, and if all of them are off, no current will flow. Let's see if there's anything else. I don't really think so. Yeah, we covered the right. I guess the only other thing to cover is how these signals propagate through. So this is the read A, right? So that propagates through my system, through this first bit of RAM, and then it propagates over to the next cell, and then to the next cell till the end here. The only other thing is this display. So like I explained in the last video, this display is just nice to have so I know what's stored inside the registers in case there are any errors. And that's just fed directly from the Q variables. I forget which one, but I believe it's Q bar because I wasn't using that one as much, so it would propagate a little bit faster. But that gets fed into this display here. Yeah, but I think that wraps it up. Hope you enjoyed.